Welcome to Lab 1 for Physics 2212 titled Charge Tapes. The purpose of this lab is to prepare two charged pieces of tape and determine the exit charge in one piece of tape after their encounter, determine the interaction between charged clear tape with other items, and create a computational model in GlowScript. The findings are shown below, where the charged piece of tape repulse each other and it will determine to be positive. The charge of each piece of tape will determine to be 1.48 times 10 to the negative 8 coulombs, and each piece of tape will determine to be deficient by 9.26 times 10 to the 10 electrons. Newton's second law states that the net force of an object is the change of momentum over the change of time, where P equals momentum and T equals time. The gravitational force represents a force that pulls object towards Earth's surface, and that is represented by F equals negative m times g in the negative y direction, where g equals 9.8 meters per second squared, and m equals mass. Coulomb's law states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of the magnitudes of charges and inversely proportional to the square of distance between them, and is multiplied by the unit vector. The Coulomb's constant is the constant of proportionality and is represented by 9 times 10 to the 9th power Newton meters squared over Coulomb squared. Here are the key assumptions for this lab. We will first treat each tip as if all the charges were located at a single point at the center, and assume that each U-tip has the same net charge. We will assume that air resistance is negligible and use the following equation to calculate the mass of tape, by multiplying by its tape length. We will also assume that the net force is 0 due to F grav and F electricity being equal and opposite. Here's the procedure for the lab. I create a U-tip by sticking one tape flat on my desk, taping another piece of folded tape on the base tape, and stiffly putting the tape on top from the base tape. I then observe the following interactions between a U-tip and another object, including my finger, another U-tip, and a charged plastic pen. Lastly, I suspended one U-tip on two objects of equal height, and then place another U-tip underneath the suspended U-tip and observe the interaction, recording the separated distance between the two U-tips. Here's the free body diagram for our system, which is the suspended tape, or tape B. Here we see that the electric force points up and the gravitational force points down. The electrical force is equal to the gravitational force in opposite directions, so we can assume that the net force for the suspended U-tip is 0. Here's the observation from the interactions for the experiment. Most importantly, we found out that the U-tip is positively charged due to the pen being negatively charged and both items attracted to each other. We also found the separation distance between the U-tip and the other U-tip, which is 0.031 meters. Here's the data I got from the experiment. I used the length and width of the tape to calculate the surface area of the piece of tape, and I calculated the number of atoms per tape by using surface area over the area of atoms. I recorded the separation distance with the magnitude of wave vector r and the mass of tape piece by using this equation to get 0.0021 kilograms. By noting that the gravitational force is equal to the electric force and that charge A is equal to charge B, we were able to calculate the charge B by using the following expression shown. And we know that there is a deficient amount of electrons because that charge is positive. We also calculate the ratio of electron transferred using the expression shown below. Here's the code used to run the computational model. This first includes the important constants such as Coulomb's constant, separation distance, and the tape mass, length, and width. In the next section, we have a few of the equations utilized to produce the results, such as the gravitational force equaling the electric force, the deficient electrons, the number of atoms per tape, and the ratio of electron transfer with the equation shown here. Next, we have the code for the position and appearance for the model as shown by the position vectors in tape A and tape B and so on and so forth. And lastly, we have the code for the resultant statements to produce a string of code to produce the results. Here are the results from the line of code. Note the resemblance to the free body diagram a few slides back. Here are the results from the computational model. The magnitude of the charge of one piece of tape was calculated to be 1.48 times 10 to the negative 8 coulombs in the model, which is almost the same value I got when I calculated it by hand. Because the tape is positively charged, there is an electron deficiency present, and for the suspended U-tip to float, the net flux must be equal to 0, as shown by the gravitational force and electric force. Possible errors could be a lack of consistent length of tape and handling of tape, and that the mass of the piece of tape was calculated based on the assumption of the equation instead of actually being measured. So by using a scale, this problem can be eliminated. The computational model does not take into account air resistance while the real life does. So by using a model that includes air resistance equation, the results could be more accurate and resemble real life. In addition, due to rounding calculations, the numbers for the measurements may not be as exact, so by keeping the same values, this could prevent this error. If electrons had positive charge and protons had negative charge, the tapes will keep the same observations and repel each other since the pieces of tape will have like charges, causing a repulsion interaction. The concept that opposites attract and like charges repel does not change when the charges switch. This will mean that the tapes would therefore repel the negative charge pen and finger, since the tape will carry a negative charge and be pushed away from the item. Instead of attracting neutral objects, the tape will begin to repel neutral objects. It is important to handle the charge tapes with as little as possible, because if the tapes are handled carelessly, the charge tape will lose its charge, causing the experiment to have a large error or just fail. The tapes have a tendency to pick up electrons as they are handled, so to remain charged, they must be handled as little as possible to avoid disruption of the experiment. When the charge tapes come into contact with my hand, the deficient electrons will be gained back.